Have you kept anywhere? Did you download videos?
I have downloaded. Now I need to take it into a Google Drive.
Okay. You joined online also, Ashwin?
Yes.
Okay. Regarding very general definition about this laser, laser is a light. That's why we are discussing about a small portion of the laser. Okay, and this is the small portion what we were discussing about in the visible region. Okay. When we talk about light of electromagnetic radiation, that means we are talking about visible region of the electromagnetic radiation. And we understood that light consisting of photons, and energy of that photon is the energy possessed by the photon is defined, or that photon will be having energy E, that is given by h nu, where h is the Planck's constant. And whatever the mathematical equations you consider where h is associated, you can assume that we are already talking in terms of quantum mechanics. Okay, this is one of the fundamental way, whatever the derivations we would have done it with h as one of the parameters. That means that there is a quantum mechanics analogy to that equation. And then we understood about that the real structure of an atom is like this. Okay, but for all our understanding, we are considering electrons are revolving around the nucleus in a circular path for the simplistic version. And then whenever electrons are moving around the nucleus, okay, they do not emit radiation according to basic models. Okay, but whenever the electron is moving from lower energy level to higher energy level, or the vice versa, okay, a radiation will be emitted out of that. Okay, radiation will be emitted out of that. Therefore, this energy is quantized. It cannot radiate whatever the energy it wants, and it cannot absorb energy whatever it wants. Okay, only in terms of quanta. That energy difference or energy possessed by the photon, either it absorbs or emits, is in terms of energy packets. Okay, one quanta of photon or two photons. Come early.
Yes.
Uh, and then we talked about the normal light. Okay, normal light. Okay, it spreads light in all possible directions, and since it is moving in all possible directions, and also uh, it ceases its existence after a long time, longer space or longer distance. Okay, but and second option is all these photons which are getting emitted are whatever the light radiation which is coming out of this kind of a incandescent bulb. Okay, we call it as a incandescent bulb or LED, whatever the light you consider. Okay, they have the light rays are incoherent. Okay, the correlation between two photons which are getting moving in this path are not very well connected to each other. Okay, either spatially as well as over the length also. Okay, therefore that kind of the characterization we call it as incoherent. Okay, and usually uh, these kinds of normal lights consisting of several wavelengths, therefore we call them as polychromatic. Contrary, okay, if I consider laser, okay, the light rays are parallel. Okay, and usually these light rays will be single wavelength, that we call it as monochromatic, and there is a wonderful correlation between two photons which are moving along this length spatially or temporally. Huh? Here we might talk little bit about this property in detail at the later case. Okay, the photons which are coming out here one after the other, there is a good correlation among these photons. There are two types of coherency. Okay, one is whenever they move in this along the length, whether they follow same characteristics, or whenever we consider, okay, this is the laser light and photons are getting emitted, whether there is a correlation between this photon and this photon. Okay, that's why there are two coherences we talked about at the later stage. One is temporal coherence, another one is what is the other coherence? Spatial coherence. Okay, over the space, over the, as a function of time, do they have correlation between two photons? Okay, those kinds of coherency is possessed by these kinds of special light, and it can be focused to narrow region and a high intensity can be produced. Having been said that, and as we considered earlier, there are spectral energy levels associated with that. Okay, number of electrons, okay, or in simple sense we consider that number of atoms in the ground state will be more compared to that of its immediate higher energy level. Okay, this, the way atoms are distributed among different energy levels is described by Maxwell-Boltzmann equation. The ratio between two neighboring energy levels is described, or they are characterized by temperature as well as the energy difference between these two. And then at that point, if you consider a thermal equilibrium, that is the case what we are having it at that point, when electrons are revolving in this particular way, in the sense atoms are distributed, at that point if I consider rho of nu is the, this is okay, rho of nu is given by u of nu is the energy density, energy per unit volume falling on the given system, and the u nu, the frequency range is between, they will be having for frequency nu and energy is given by h nu, and if E1 and E2 are two energy levels such that if E2 and E1, at that point this incoming photon either that can be used to make this atom to go upper level, or it will be at the higher level and this photon will make it to bring it down. We discussed about this concept in detail in the last class. Therefore, during that process there are three processes which can happen. Okay, one is absorption. It is also called as induced absorption. Second one is, if once atom goes to higher energy level, immediately they radiate energy, that is called spontaneous emission. If atom is in the higher energy level and incoming photon can make it to forcibly to come down to the lower level, that we call it as stimulated emission. And then we got an equation for these kinds of, we have to get equations corresponding to these three processes. Let us consider the first case, absorption. It is also called as induced absorption. Okay, whenever incoming photon is hitting the atom which is in the ground state, okay, it makes it to go to higher energy level. That happens only when the incoming photon's frequency or energy, that is E, is exactly equivalent to the energy difference between two energy levels. Okay, therefore the frequency of absorption is given by E2 minus E1 by H. The rate of absorption, obviously the rate of absorption means, rate means with respect to time, how many photons can be absorbed by during this process, does depend on what is the number of atoms present in the ground state. Okay, and that the general definition for this rate of absorption is given by how well, okay, how how fast number of atoms in the lower energy level would change as a function of time. dN1 by dt is the rate of absorption, and that depends on how many number of atoms are there in the ground state, and also what is the energy density which is falling on the given system. Therefore, R12 star depends on N1 as well as U nu. Let us write a mathematical equation by removing this proportionality symbol with another coefficient of proportionality. Okay, that one we call it as B12 is constant of proportionality. Okay.
Given that the star indicated for something.
Yeah. Here this is B12 is called constant of proportionality. It is basically Einstein's coefficient. We call it as coefficient of induced absorption or absorption. Okay, it is called UL2. And here, as you know that our rate is generally represented as R. Okay, suffix represents that transition is happening from energy level 1 to energy level 2. Okay, and this rate, this star represents this rate we are defining in the presence of external radiation. Okay, this process can happen only in the presence of external radiation. That's why we are using this symbol notation star. Okay, and suffix represents whether transition is going from 1 to 2 or 2 to 1. Second one is spontaneous emission. Now you assume that your atom is already in the excited state by some other way. Okay, at that point what happens? Here, though the heading is given as interaction of radiation with matter, okay, here at this point the radiation need not to interact with the matter at all. In this case, the moment atom goes to higher energy level, this higher energy level will be having it is an unstable state. Unstable state means it is sort of very simply or very vague way of understanding this unstable state is like when you throw a ball upwards, it comes back. For different reason it comes back, but you can assume that it cannot stay over there. It is in the air. Okay, like this energy level is an unstable state. That means to say that that energy level does exist. It is not like in our air, but the lifetime of this energy level will be in the order of nanoseconds or even less than that. Okay, therefore immediately once it goes up, it comes back to ground state naturally. That we call it as spontaneously. The moment it goes up, it comes back naturally or spontaneously. That's why we call it as spontaneous emission. And whenever the spontaneous emission also, we know that energy should be conserved. Okay, whenever it has absorbed certain energy to go up, it has to release the same amount of energy whenever it is going out. Then whenever this electron or this atom is jumping downwards, it releases photon, and that photon's energy is exactly equivalent to, because it is moving from this energy level to this energy level. Therefore, it has to give out the energy that is equivalent to E2 minus E1. Okay, that is exactly similar to the way it absorbs. Here it is emission. This emission is happening simultaneously. That's why, and also simultaneously means spontaneously. That's why we call it as spontaneous emission. Okay, and the key point what we need to understand here is, for this spontaneous emission to occur, it does not require the presence of radiation. Okay, though we are discussing under the heading interaction with matter, okay, really I don't need my external radiation to interact with matter. Okay, the moment it goes up, immediately it comes down to the ground state. At that point, it releases energy. Okay, and most of the cases, whatever you are considering here, all these lights, what you are seeing, our incandescent bulbs are incandescent bulbs. Okay, tube lights. Okay, they are all because of this process. Okay, somehow by some other method we make these electrons to go up. Okay, in the tube. Okay, you can just Google it, how does it work, you will get and you will understand it. Therefore, most of the processes what we use, they follow this process. While emitting that radiation, whatever the amount they absorb by some other way. There are different ways atoms can go to higher energy level. Okay, that way then they coming down to lower state, thereby emitting radiation of frequency mu. Okay, now does not require, and whatever the spontaneously emitted photons will be incoherent. That means that all our lights, okay, this process does happen. Okay, at that point, all these photons, one photon goes this way, another photon goes this way, another photon. Whenever we are having more number of atoms in the higher energy level, okay, each transition will give rise to one photon. But all these photons, whatever the energy they release, okay, they move in different directions. Okay, and therefore there is no correlation among different photons what they are coming out of the given system. And then let us write that, okay, can you write that what is the rate of spontaneous emission? Okay, this is the rate of spontaneous emission. If I want to write, how do you write? Okay, the representation is given by, okay, let us use the same word R, R 2 to 1. It goes beyond the screen. R 2 to 1. Okay, this is somewhat. Okay. There is a problem with this black screen. It is staggering. There I cannot see. Okay. Then this is given by R21. Do I have to put star here or not?
No, it's not radiation.
Yes, it is not interacting with external radiation. I don't put star. And what are the things it would depend on? R21. N2, because if more number of atoms are there in the higher energy level, the number of transitions will be more. Otherwise, it is less. Therefore, the rate of spontaneous emission depends only on the number of atoms in the excited state. Therefore, dN2 by dt spontaneous emission can be written as R2 to 1. Okay, that can be written, proportionality symbol can be removed by adding A21 N2. Write down. Are you writing? You? No, I am asking you. What's your name? Huh? You have to keep writing it. Okay? That's like short notes. Okay? Some of the important points you might miss it. Okay? If not all the description.
We have to go into the room, then we will have this video again, then we will write.
Yeah, you can do that, but whenever you are sitting in the class, okay, some of the important points, you know what to write, what is already present here. Okay, that star and other things, if you don't remember, okay, you won't remember that. Okay, that in your own vague way you can write it. I don't mind. That's why we don't give notes in that fashion also. Okay, therefore, rate of spontaneous emission depends only on the number of atoms in the excited state, and there is a proportionality symbol. Okay, A21 is constant of proportionality. It is also called as Einstein's, and these relations were proposed by Einstein. Okay, as I told you that whenever there is an H factor, okay, that is already quantum mechanics. Okay, and you know that he is one of the, along with Planck, Schrodinger, he is also one of the pioneers in developing the quantum mechanics. Therefore, A21 is constant of proportionality, are also called as Einstein's coefficient of spontaneous emission A21. Okay, please remember in the earlier case, what was the equation we wrote it for dN1 by dt for induced absorption? What was that?
B1.
Yes, that is the notation was B, here A. Okay, we should distinguish. Okay, and then A21 is called the constant of proportionality, Einstein quotient for spontaneous emission. Okay, now we will move on to the third case. What? Assume that your atom, okay, this is important concept, you can write down later. First, pay attention to this. Assume that this is the what is this? Okay. Now consider atoms are in this excited state by some other means. Okay, it need not to be. Okay, of course, absorption has to happen to make atoms to go to higher energy level. But let us assume that our by default atoms are already in this state. At that point, my external radiation does interact with the matter where we have two energy levels, and the population in these two energy levels is given by N1 and N2. At that point, our external radiation does interact with this radiation, with this matter. Okay, and the incoming photons frequency is also equivalent to nu, that exactly matching with that of the energy difference. Okay, as it is given here, this incoming frequency is exactly equivalent to this E2 minus E1 by H. At that point, what happens? This incoming incident radiation stimulates these atoms which are present in the higher energy level to make them to go down.
So if they absorb any energy, they need to go out now.
Again, that's why we are very much specific to the case that we are applying radiation in such a way that this nu is exactly equivalent to that of this energy difference. Usually in any matter, okay, we don't have two energy or two sets of energy levels, they will be having same energy difference. Okay, we have understood in our first orbit, right? In our Bohr orbit also, Rn depends on radius and some other parameter, principal quantum number. The energy difference keeps on decreasing as we move on. Okay, therefore, the energy difference is not always constant. Only among these energy levels, energy difference is constant. And you can switch off this fan or reduce the speed. Fan. Or that fan speed, you can slightly decrease. No, don't switch off. Decrease the speed. Okay. Okay. Here, what is happening? I am applying radiation in such a way that the incoming radiation is forcing this atom to move to lower energy level. Okay, that is, it is stimulating that fellow to go down. Okay, and whenever this atom comes back, it is not only stimulating, okay, this atom absorbs this energy also. It absorbs this energy and it comes down. Then whenever it comes down from higher energy level to lower energy level, whatever the energy it absorbs, that has to be emitted out of the, whenever it comes down, it has to emit that radiation, right? What is the problem with this? Okay, it has to emit that radiation. On top of that, there is already energy difference between these two energy levels, E2 minus E1. Because it is moving from here to here, it has to emit same amount of frequency whenever it is coming, therefore another photon is also emitted. Now, instead of emitting one photon, the stimulated emitted atom will emit two photons. And goodness of this are Goodness of these two photons are that because these two processes are happening simultaneously. Okay, and transition is only one transition. Okay, two photons are emitted. Therefore, there is a good correlation between these two. Okay, it is not that
Excuse me,
randomly one. Yes.
sir. I didn't understand why two photons are emitted when one photon is incident, sir.
See, here, whenever assume that, okay, if I want to give vague answer or simple layman's answer is that, okay, somehow you are already rich. Okay, like that your mom or somebody has already given you pocket money of 100 rupees. Okay, you are already super excited and you want to purchase. Okay, anyway, not 100 rupees, 1000 rupees. Okay, for you to little excited. Okay, 1000 rupees is already with you, but poor fellow, your father doesn't know. Okay, he will also come and he will also give another 1000 rupees as pocket money. Okay, and then what happens? You don't reject that, right? Those who are sitting over there, then you take from both of them and you empty your pocket. Okay, whenever you are emptying your pocket, you have to empty both contributions, right? Your fathers and mothers. Here, one contribution is because this is father's contributions. Okay, but somebody, okay, previously itself your mother has already given money, that's why you are already happy. Okay, you are in the anxiety state. Therefore, at this point, you have to give out or you are spending more energy. Okay, and at that point, you are purchasing two equipments or two gadgets which are equivalent to 1000 each. That time, you can always go and get the same equipment. Okay, same model. Okay, you don't have to wait for that. Okay, two pieces you can purchase. They are 100% identical to each other. Okay, from the same batch, that particular whatever the gadget would have been prepared. Therefore, it is emitting two radiations. In this case, if you come back to this particular example, your atom is in the higher energy level, and at this point, let us come back. When does this happen? When does that spontaneous emission happen at the later stage? Okay, now assume that atoms are already in the higher energy level and your incoming photon is coming and hitting this atom. And then whenever it is hitting, this entire incoming photon's energy is absorbed by this atom which is present in the higher energy level and it jumps to lower energy level. Whenever it jumps to lower energy level, naturally there is an energy difference from this E2 minus E1 is already gained by the atom. On top of that, incoming photon is also incident photon's energy or frequency exactly equivalent to you. Okay, therefore, father also given 1000 rupees, your mother is also given 1000 rupees. Both of them, you will go to what is that? In our neighboring place is Maleshwaram. Okay, immediately, okay, spend entire money. Okay, you will get identical ones. Okay, and your friends do not notice even if you lose one. Every day you are wearing the same, probably fancy dress or something like that. They are identical to each other. They might be wondering how come you are wearing and it is not becoming dirty. Okay, that way you are getting two photons. And goodness is actually it's a good example. Okay, you are getting identical one. Therefore, there is a good correlation between these two photons because the process is one, but two photons are coming. Therefore, they are coherent in nature. And obviously, because transition is happening from E2 to E1, they are monochromatic in nature. Obvious, right? Because energy difference is same, mu is same, only one mu. Therefore, the emitted photon and the incident, and also another good example here is the incident photon. Whatever the photon which is okay, here this photon is incidenting on the atom which is in the higher energy level, right? This photon and the emitted photon will also be in phase. Okay, whatever the photon which is coming, okay, there is a good correlation from here to here also. And top of that, this one to this one also we have good correlation. Okay, therefore, whatever the photon which is coming here, they are all three photons are in phase in principle. Okay, therefore, we are having very coherent source as well as, okay, and incident photon and outcoming photons are coherent in nature. And hence, okay, you understood this basic funda here. Okay, and now let us try rate of stimulated emission. Okay, that is R. What is the symbol I have to write? R 2 to 1, and it is happening in the presence of external radiation. That's why star is there, and it depends on what are the things it depend on. Yeah, it does depend on N2. Yes, it does depend on energy density. Okay, if more, it is very much similar to that. 1000 is always same. Okay, how many thousands your father? Okay, is it not? Okay, you can get so many dresses. Okay, that's why that energy density is also important. Okay, and how excited and how willing or how many people are there if you consider. Okay, therefore it does depend on N2 as well as UV. Okay, therefore rate of stimulated emission depends on number of atoms in the excited state and energy density of the EM radiation. Therefore, mathematically I can write it as it depends on N2 as well as UNU. In the combined effect, we can write the dN2 by dt first stimulated emission. Please remember, in the previous spontaneous emission, again I am only talking about how well number of atoms in the higher energy level would decrease as a function of time. Therefore, we are still writing dN2 by dt. Just to distinguish, we are writing suffix stimulated emission. In the previous one, we wrote it as spontaneous. Therefore, and we have star also. And again, we have a constant of proportionality. That constant of proportionality, again, we switch back to the term B. Because B represents in the presence of external radiation. Okay, A represents in the absence of external radiation interaction. Okay, therefore, B21 is called constant of proportionality. Okay, it is also called as constant of proportionality, again Einstein coefficient for stimulated emission. Okay, we are going to write it at the end, all three.
So here you can explain that, like space coherent and time coherent. Here you can distinguish one.
No. Before that, we have a lot more things to do. Okay, let us get back to that at the later stage. Okay, as I told you that this laser itself our AMOP student like atomic and molecular physics MSc students, we have a very good this kind of a book. Okay, we are telling what is important aspects corresponding to that. Okay, let us understand up to this point, but we do talk about the coherence of the later stage. Okay, now you understood this, all of you. Okay, this is very important. Okay, now let us consider Einstein coefficient. Now we understood all three processes. Okay, and assume that whenever we consider matter, it is not one atom. Okay, there are several atoms do present in the matter. Therefore, we have to consider at equilibrium what does it happen. Okay, and we have large number of atoms present, and all of them are whenever I take a container, that container's temperature is T. At that point, okay, please pay attention here. You can write that. Okay, the key point. All these three processes, okay, at thermal equilibrium. Okay, for example, light is falling on you. Okay, all three processes like spontaneous emission, spontaneous emission, stimulated emission, absorption, all of them will occur simultaneously because radiation is continuously falling on you. Okay, it doesn't distinguish whether one person is excited or it is in the ground floor. At thermal equilibrium, everybody should be same, right? Okay, constantly this radiation is falling. Okay, it is only in the matter. As we know that thermal equilibrium are at any one particular temperature. Okay, according to Maxwell-Boltzmann equation, number of atoms in different levels is already gone by Maxwell-Boltzmann distribution. Okay, that rule should be satisfied always. Okay, it is not that only spontaneous emission or absorption occurs first and then spontaneous emission or stimulated emission, they would occur later. Okay, all these processes do happen simultaneously. Okay, you will be absorbing energy, leaving out, absorbing and leaving out. Okay, all these things are continuous processes. Okay, and the way we always learn new things, we forget old things and whatever we have learned it. Okay, if somebody asks you that what is the so and so reaction or something like that, you would have studied in your 10th standard, you don't remember. Like you have joined your engineering physics, and if somebody asks you that what is algae and what is the constants of that, you may not remember now. In the biology, like that, we understand, leave out. Understand, leave out. What is important, we keep it. Like that, this process also, it is a continuous process. We keep all these processes are happening simultaneously. That demands that, okay, the mathematical pictorial representation is that absorption is also happening, spontaneous emission is also happening, stimulated emission is also happening continuously and simultaneously. Okay, and at thermal equilibrium, if this all three processes to happen simultaneously, at thermal equilibrium, what should happen? I have to consider that upward transition, okay, rate of upward transition should be equivalent to rate of downward transition. Is it not? Because all three processes should happen simultaneously and also our energy level system should follow Maxwell-Boltzmann equation. Okay, all three processes are happening. Therefore, how many rate of absorption should be equivalent to, or rate of upward transition should be equivalent to rate of downward transitions. Okay, and how many atoms go up should be equivalent to how many number of atoms come down. Okay, all of you got this point? Okay, this is the important point where this is one of the major derivation what most likely we ask in our exams. Okay, get an expression for so and so in terms of Einstein coefficient. A few 4 or 5 marks we ask one of the processes. Okay, that's also possible. Okay, now we first independently discuss three phenomena which can happen. Now we are coming to the thermal equilibrium. At that point we understood that rate of upward transition should be equivalent to downward transitions. Okay, that creates, let us assume that, let us consider two energy levels. Okay, N1, the energy levels where N1 is the number of atoms in the state E1 and N2 be the number of atoms in the state E2. Okay, and let us say whatever we had it in the beginning. Okay, let rho of mu is given by u nu is the energy density, that is energy per unit volume of the photons of frequency nu and energy h nu. Okay, and let us write the, now summarize all these processes in one slide. Okay, absorption rate. What is absorption rate? R 12 star, okay, dN1 by dt with absorption is given by B12 N1 Unu. Okay, we already know this. Okay, you can label it as 1, 2, 3 also if you wish. Okay, second one is, I just reorganized it. Okay, let us assume that stimulated emission happens. Okay, and stimulated happen Stimulated emission, again that is also I am using a star because these two processes are happening in the presence of external radiation. Therefore, dN2 by dt stimulated emission is given by B21 N2 UU. Okay, and third process is spontaneous emission, that is given by dN2 by dt, the spontaneous emission R21, and that is given by A21 N2. It doesn't depend on external radiation. Now, here we will consider that what are the Einstein coefficients here, whatever the B12, B21, okay, and A21 all are called as Einstein coefficient for as it is given. Okay, here in this slide I would have written that stimulated, please pay attention here. My pen doesn't want to come here. Okay, here it is called as stimulated absorption. This is also in some textbooks they used, or we can write it as induced. It is just to indicate that it does happen in the presence of external radiation. Something else will influence your transitions to occur. They are called as induced absorption, Einstein coefficient for stimulated emission, and spontaneous emission respectively. Okay. Is it clear up to this point? Hello?
Yes.
Okay. Now, I think we can take it from next class. Okay. At this point, let us try to have that. Okay. This at equilibrium, number of atoms undergoing absorption should be equivalent to number of atoms undergoing emission. Here, the derivation starts from this point. Okay. Okay. I hope all of you are able to follow. Hey, it did not ring the bell, right? Okay.